Good afternoon, everybody, and welcome to the first Train Talks at 12 webinar. This will be the first in a series of short 30-minute sessions that we've got planned, looking at different aspects of friction management and how it can be used to benefit rail operators by mitigating friction-related wheel and rail issues. So we have further sessions planned in the coming months, and these will take a deeper dive into some of these issues and solutions that I'll be introducing and touching on today. I'm Jackie Butterfield. I am the lead applications engineer for LB Foster in Europe and support Update, who is our European sales manager. So Zoe's going to keep an eye on the chat and any questions that you might have. If you do want to ask any questions, just pop them in the chat and we'll deal with them at the end of the presentation. So this first session is very much going to be a broad introduction to friction management, starting at the beginning with why do we need to control friction in the wheel-rail interface, and what are the damage mechanisms and issues that can be mitigated by employing a friction management regime. And they'll go on to a broad definition of friction management and what factors do we need to consider when we are developing and implementing an effective solutions-based approach to friction management. I'll then briefly introduce the options for application methods and equipment and consumables, and give you a sneak peek of the upcoming webinars that we've got planned. And then finally, an invite to those of you who will be attending Innertrans this month to come and meet us on our stand. So firstly, why do we need to control friction in the first place? And control is very much the correct term that we need to use in this context. Friction is required for movement to occur. Without friction, there would be no movement. Acceleration and braking would not be possible without a certain level of friction. There's been much debate about what this absolute level of friction is, varying from 0.15 upwards. So for the purposes of these webinars, we are basing that minimum level on 0.2. So in the wheel-rail interface, uncontrolled friction can lead to a number of damage mechanisms. And we have some pictures on the right of examples of those. So we have excessive wheel and rail wear, rolling contact fatigue damage, corrugation damage, curve squeal and flanging noise, high lateral forces, potential safety issues, including wheel climb derailment and lateral force L/V derailment, higher fuel and energy consumption due to excessive resistive forces, and also at the low adhesion level, the incidence of wheel flaps, signals passed at danger, and also braking issues. Just as an illustration, the difference in wear rate and therefore wheel life between a poor and a good friction control regime can be a factor of 20 or more. And we found this in various case studies and real life issues that we've had over the past 30 years dealing with friction management at LB Foster. So what controls the friction in the wheel-rail interface? So at a fundamental level, we're talking about a steel wheel in contact with a steel rail. However, the two surfaces, which are relatively rough on a macro scale, are not, strictly speaking, in intimate, clean contact. So between the wheel and the rail, we have the third body layer, which is a layer of material which separates the wheel and the rail. And it's this layer, which is only a matter of a few microns thick, shown here on this electron microscope image, which determines the wheel-rail friction. And it does this by the characteristics of the third body layer accommodates the velocity differences between the wheel and the rail, i.e. the creep and slip in the wheel rail interface. So this third body layer is made up of a number of materials which vary in proportion and composition at any one time. So these are iron oxides, sand, other organic and inorganic particles, water, grease, oils, brake dust, wear debris. So the composition of this layer varies constantly from minute to minute and from meter to meter along the track. So wheel rail friction depends entirely on the shear properties and composition of this third body layer. So looking in more detail about this third body layer, each component of this layer will bring its own characteristic level of friction. So working from the top, iron oxides under a dry condition, so we're talking about Fe2O3, the most common iron oxide, will characteristically give a coefficient of friction of between 0.6 and 0.7, so a high coefficient of friction. However, if you then add water and humidity into that equation, then that will drop to below 0.2. So there's a fundamental difference in the environmental and the climate in terms of the properties of the third body layer. So other materials such as oil and grease will go anywhere between 0.05 to 0.2, heavy rain 0.2 to 0.3, and inorganic and organic contaminants as well will have their own varying levels of friction. Obviously, organic contaminants such as leaf layers will give a very, very low coefficient of friction, whereas sand, clay, ballast debris will give typically a higher coefficient of friction. So this mixing pot of the third body layer is changing all the time. And the best way probably to illustrate is the classical bathtub model. So you have a bathtub which represents the third body layer, and into that you have an intermittent on-off stream of traffic levels, environmental conditions, brake debris, wear particles, sand, friction modifier materials, which are then mixed together in the bathtub under the influence of heat. Chemical reactions take place, and out of the drain holes in the bathtub come various chemical reaction products, solid particles, liquids, excuse me. So this third body layer is changing all the time, and therefore the railhead coefficient of friction is also dynamic and changing all the time. So in terms of the definition of friction management, our established and agreed definition is the deliberate introduction of materials into the third body layer between the wheel and rail to influence the frictional behaviour. So we're adding products in there to control that level of friction, to mitigate those damage mechanisms, and to give us the desired outcome that we want. So looking at the range of friction levels that we typically get, with a dry rail condition, we're looking at upwards of 0.5, up as high as 0.7, 0.8, depending on the environmental conditions. For example, in the Middle East, friction levels can be up as high as 0.8, even up to 0.9. And then we have different target levels of friction that we want to achieve on the railhead and the wheel tread. So just by illustration, on the rail head, we want to maintain this intermediate level of friction somewhere between 0.3 and 0.4. And this is to ensure that there is no impact on traction and braking. So as I said earlier, the minimum level that's required really for traction and adhesion and braking is around 0.2. So we want to achieve a level on the top of the rail, on the rail head, somewhere intermediate between 0.3 and 0.4 to ensure that operational efficiency of the rail is not affected. On the gauge face and the gauge corner of the rail, we want as low a coefficient of friction as possible. in order to mitigate those wear and damage mechanisms there. And so we're looking at well below 0.2. So the European standard EN 15427 dictates a level for lubricants of below 0.15. So because we're looking for two different levels of friction, we're effectively looking for two or more different types of products to apply into the wheel rail interface. So we have our materials that we will use for gauge face, wheel flange and back of flange lubrication. And these are applied and will have the impact of reducing rail and wheel wear on the gauge face, the wheel flange, and also any check rail or guardrail that you have in place. They will mitigate against rolling contact fatigue development, particularly gauge corner cracking for the gauge face. They will also mitigate against flanging noise and also against wheel climb derailment risk, and also will help with fuel efficiency as well by reducing the resistive forces in curving. Applying materials to the top of the rail or to the wheel tread will also have an impact, and these will be on top of rail and wheel tread wear. Again, rolling contact fatigue development, head checks, corrugation damage, top of rail squeal noise in curves, lateral forces. They will also have an indirect effect on flanging noise. As you're lowering the coefficient of friction, you're also lowering the lateral forces, so therefore you're improving the steering of the vehicle and reducing the amount of flanging contact. So therefore, if you're reducing the contact, then you're reducing the source of that noise. Also, it will affect fuel efficiency as well by lowering the resistive forces in tangent and in curving, and reducing the risk of derailment potential due to high lateral forces. Because you're improving the steering, you're also improving the hunting characteristics of the vehicle to some extent. And then finally, using traction gels and traction enhancers, you're recovering adhesion due to low adhesion conditions, due to either autumn conditions, either damp rail or leaf layers, or even railhead contamination. So the overarching goal for any effective friction management is to maximize the benefits that you get from the friction management regime. So we're looking very much at a solutions-based approach to friction management. And so to be truly effective, it needs to take into consideration the following. So firstly, the technical details of the system. Oh, pardon me. So what are the issues that we're facing? Are these issues localized on a particular section of track, or are they widespread? How severe are they? How accessible is the track or the vehicles in terms of maintenance and installation? And how practical is a friction management solution? Look into the system details, the age of the system, also the organizational characteristic. Who owns the system? Is it separate ownership of the track and the vehicles as it is in the UK, or is it under one ownership? Is it an open or a closed system? Is the track shared by other types of vehicles or one single type of vehicle? What of those vehicles? What are their characteristics? What is their configuration? What is their wheel profile, their wheel rail dynamics? And also to look at the track. What is the track characteristics, the length, the number of curves, the severity of a curve, and also the environment. Finally, the organizational characteristics. So who are the people involved? Who are the team? Who sets the budget for friction management? And who benefits from the friction management program in terms of the lower maintenance? Also look at the maintenance strategy as well in terms of the timing, the people, the staff, What is the maintenance regime? Are there any operational constraints? Other constraints in terms of space for location of units, or are the constraints in terms of time? Is it a 24/7 operation? Does that give you limited time for maintenance and for installation of equipment? So all of these factors should be taken into consideration when designing a friction management solution. And the friction management solution needs to be integrated completely into the rail operation environment. So it has to take into consideration any operational constraints, the operational regime, and also needs to adopt the best practices for friction management. But it's not just looking at the equipment that is used and the consumables. It also includes the maintenance regime and the filling frequency, and probably of most important, a monitoring and measurement regime to enable you to actually measure the benefits that you're getting from the friction management program. Because if you can't measure and validate the benefit, then what is the point in employing the friction management in the first place? So moving now on to the hardware. So in terms of the two areas, we have a number of options for applying friction management products. So for the gauge face, we have a trackside option. So trackside hardware that apply product to the rail. We have the option of onboard solid sticks, which apply product to the wheels. And we have onboard spray systems, which apply liquid products to the wheel flange. Also for the topper rail, we have trackside solutions as well, onboard solid sticks and onboard spray systems. So really we're looking at the right solution for the customer in terms of looking at localized issues as opposed to widespread issues, and that would drive you down either a trackside or an onboard solution. And then we're getting into the details of the consumables that you want to use in the system. Are they solid sticks or are they liquid products? So there are many, many ways to apply friction modifiers and lubricants into the wheel rail interface. So looking now at those consumables, so for trackside, for the gauge face or wheel flange, you're applying greases. For onboard solid sticks, you're applying flange lubricating sticks, or also the option is if you have a grooved rail or a check rail guardrail system, you can apply stick to the back of flange to combat back of flange wheel wear and noise as well. And in terms of the onboard spray, you have a number of commercially available onboard oil spray systems, which will spray a fine spray of oil onto the wheel flange. At the top of rail and wheel tread, again, we have trackside options, which can apply friction modifiers or traction gels for adhesion enhancement to the top of the rail. For onboard solid sticks, we have tread sticks, which provide an intermediate coefficient of friction rather than a lubricating level of friction below 0.15. And then finally, we have the onboard spray systems, which can apply friction modifiers from the vehicle directly to the top of the rail. So again, with the different types of hardware, we have many different types of friction modifiers and lubricants available on the market. So now just going into a little bit more detail in terms of the hardware. So in terms of trackside friction management application, this is going back to the very, very simple systems. So these are the legacy systems, the mechanical lubricators. So these are only for gauge face lubrication. So these are very simple mechanical devices which are actuated by a plunger, which is applied to the field side of the rail. The wheel presses the plunger, opens a valve, and then that allows the passage of grease from the spring-loaded yellow canister out onto the applicator bars and onto the rail. So it's a simple system. It's fairly easy to maintain. However, it has a low grease capacity. And so you're looking at frequent refilling of these grease canisters. You also have no or little control over the grease output because every time the wheel passes, the valve is opened and the grease is applied, which may be over applying the grease and you're wasting product that you don't actually need. However, as far as LB Foster are concerned, this system, the mechanical system, is obsolete, but we do still sell some minor spares for the existing units still out on the network. In sophistication slightly, we have hydraulic actuated units. So these are cost effective, again, a very simple system and actuated by a hydraulic actuator. So again, a plunger which is attached to the field side of the rail. The wheel actuates the plunger, which then pressurizes a hydraulic line, which then opens the pump, and grease is applied through the hoses to the bars. Again, it's a simple system which outputs grease every time the plunger is actuated. There is limited output adjustment. So again, you may be over applying grease or wasting product. There is a limited output adjustment by a regulator valve on the pump, which can be used to fine tune the output slightly, or you can increase the height or decrease the height of the plunger to give you a larger or a shorter stroke to give less or more grease. These units are quite flexible in terms of the capacity. So start from a small unit at 12.5 kilos up to a larger one at 37.5 kilos, but you can couple two tanks together to give a 25 or a 75 kilo capacity tank. The other advantage of these is that you can actually embed them in the ballast. So you can bury them to give a very low height profile, so you can fit them into areas where you've got tight gauging tolerances. So then we move on to the electric units, and we have a number of different types of units here on the screen. So these give a much greater control over the output of grease. So feature a product tank, a digital control box, which allows you to set a precise pump time and axle count for each activation and application of grease. Typically, they are solar panel powered with a 12-volt battery, but they can be AC mains powered as well. So these are seen as the best approach and the most sophisticated solution for gauge face lubrication, and also for top rail friction modifier for trackside. So one electrical lubricator can replace multiple mechanical or hydraulic lubricators due to the increase in efficiency. And to get the grease onto the grease or the top rail friction modifier onto the rail itself, we have a number of designs of applicator bars. So these are clamped to either the gauge face of the rail for gauge face grease, or to the field side for top rail friction modifiers, or to the check rail. So the top right picture is a check rail bar applicator. So these have multiple distribution ports to distribute the grease effectively. They can come with a grease trough or also with a grease guide, which will assist in keeping the grease against the gauge face. can be applied, as I said, to running or restraining rails, and they're easy to install and maintain. And then we have the traction gel applicators, which are a slightly different design, but work in exactly the same way with a product tank, a control box and a pump system, and apply traction gel onto the top of the rail. Onboard solutions, we have the solid stick solutions. So here we have an example of a triple system. So we have a wheel flange stick applicator, a tread applicator, and a backer flange applicator as well. So these are a very simple mechanical system with a constant force spring in the back of the applicator, which holds the sticks against the wheel. No electrical or pneumatic connections are required. The system is self-regulating and is very, very easy to install and maintain. And then we have, so the key components of the system are an interface bracket, which connects the applicator to the bogie frame of the vehicle, and the applicator which houses the sticks. And then we have our onboard topper rail and wheel flange spray systems. So wheel flange oil spray systems are well established. L.B. Foster doesn't supply these, but there are a number out there on the market. But topper rail spray systems are a newer technology and give the same benefits as topper rail trackside units. However, the maintenance is carried out in the depot. So in terms of safety, these are much safer systems, and they can be controlled to spray where and whenever they are required through a sophisticated control system. The benefits that can be achieved, a couple of tables here on rail wear and wheel wear reduction. So we have typical reductions in top of rail wear and gauge face wear for gauge face systems and a combination of gauge face and top of rail friction modifiers. So you can see the range of benefits there that you can have, and also on the wheel wear. So up to 95% reduction in flange wear and around 50 to 60% in tread wear. So finally, in summary, I've gone through why do we need to control friction in the first place? What are the damage mechanisms and issues? What is the rough definition of friction management, and how do we approach it from a solutions-based approach? A brief walk through the application methods and consumables. So what's coming next? So as I said, this is the first in a series of webinars. So we've got the next few webinars are going to take a deeper dive into some. So our next webinar is going to be on Wednesday, the 2nd of October, which is on wear and rolling contact fatigue. And then we're going to follow up in November with noise, December with corrugation damage, January with low adhesion issues, February with energy consumption, March with derailment issues, and then finally in April, a look at validation and trials best practice. So how do you measure and validate your friction management program to get the best out of it? So finally, if you're visiting Innotrans in the next couple of weeks, please come and visit the L.B. Foster stand in Hall 25, booth 285. And that is me. So if you have any questions, Zoe, do you have any questions in the chat?
No questions in the chat, but we've got 1 minute left if somebody's burning to ask Jackie anything while we're here.
Yeah. I mean,
Stephen Wilson, is rail squeal, I'll read it out. Is rail squeal only created from the railhead rather than the gauge face?
Yeah, I mean, there's two different types of high frequency noise, and obviously when we get to the noise session, I'll go into a lot more detail in terms of the mechanisms of these. But squeal is a very kind of broad term. So high frequency noise can either be generated from the top of rail, so we tend to call that top of rail squeal or curve squeal, and that is an oscillating mechanism. So that's related to stick slip oscillations in the wheel rail interface. Flanging squeal or flanging noise is a different frequency of noise, but it's also a different mechanism. It's simply the contact and the kind of grinding of the two metallic surfaces together. So there's a few kind of terminologies around squeal, but when we get onto the noise webinar, I'll go into a lot more detail on the different mechanisms and the differences and the different solutions for both. So please tune in for that one.
We have a poll as well, don't we, Jackie?
Oh, yeah. I've just put a quick poll together, so I would really appreciate it. So of the kind of mechanisms that, certainly, Stephen, I will go back. Just bear with me. So I'm just going to share this poll with you. So these are the damage issues that I've talked about this morning. So if you could just tell me, just vote for which is your highest priority. If you just bear with me, let me minimize that. I will. How do I get back to my presentation? I can't work out how to get back to my presentation, Zoe. This is not.
Well, that's fine. We can share
Yeah.
We can share the slides afterwards and put all the dates in some of the feedback emails that we'll be sending out as a result of you all attending this. And it is it's good to say as well that if you've got any interest in anything that you've seen in the webinar, as Jackie says, we've got a series of webinars over the coming months, but if you've got a burning interest or issue that you think LB Foster will be able to help with, we'll also be sending out our contact details. I'll put them in the chat regardless, and you please get in touch with us and we'll see how we can help and support you. So far, out of 18 people still here, we've had 3 responses on the poll, so it just takes a couple of seconds to press the buttons. We'd really appreciate it, because this will form the curriculum for the rest of the webinars, you see. So if you're interested in viewing more, then let us know what you're interested in, and then we can tailor it a bit to you.
Yeah, the noise one is December, so I think it's 11th of December is the noise one. But what you will get after this, immediately after this webinar, is you'll get a link to the recording, and there is also a registration link for the webinar in October as well. So what I will do is ask Meredith, our marketing support, to actually put the full list of the dates in the follow-up emails, so you can actually plan those ahead. So rather than just getting the next one, we'll ask her to put the whole dates in there as well, so that you can pop those in your diary. So yeah, thank you so much for attending. I hope you found it useful. It's been very much a high level one today, just as an introduction, but we will be going into much more detail in the following in the following webinars.
Just had one more chat, Jackie.
Yeah, I think somebody's having problems with the poll. Right, okay. Network Rail doesn't like polls in Teams.
That's fair.
Okay.
Enough. Lovely.
Thank you very much.
Thank you, Andrew.
All right, thank you.
See you all in October, and hopefully some of you are in a trance.
Yeah, okay. Bye.